to our special Wednesday seminar. I know that, from scheduling and so forth, with these normally being on Thursdays, I appreciate you being able to shuffle your schedule. I do want to introduce our speaker for today. Our speaker is Dr. Benjamin Beeler from Idaho National Laboratory. He is a computational scientist in the Computational Microstructure Science Group in the Fuels Modeling and Simulation Department.
Yeah, we have very long names for things.
That's why I got the sheet. That's why I got this 8-point font cheat sheet that someone with way better eyes than I apparently printed it up. Most readers. I might need. I don't know. I've tried those on before, and those don't. It's like a fishbowl. I can't do that. So he has degrees in. Dr. Beeler has 3 degrees in nuclear engineering, received in 2008, 2011, and 2013 from Georgia Institute of Technology. From his time at Georgia Tech, he then had completed a postdoctoral study. It was a joint appointment between UC Davis and the University of California, Berkeley. His professional interests are atomistic description and evolution of nuclear fuel and structural materials, with experience in interatomic potential development, particularly related to uranium and uranium alloys. Since 2015, his primary focus is within the Marmot team is the investigation of metallic nuclear fuels, utilizing density functional theory, molecular dynamics, and phase field methods. So hopefully by the end of this talk I will know what the whole back half of that paragraph means, and I'm looking forward to this. So thank you very much for being here.
Thank you. So sorry about that. If I knew that he would read the whole thing, I would have made it 2 sentences long. Sorry about that.
My eyes are still open.
So thank you all for coming. Good afternoon, everyone. I'm making the assumption that a lot of people won't know the kinds of stuff that I'm doing. So I've tried to make this a bit of a general overview. But if you have questions as we go through, don't hesitate to stop and ask. I don't know if you all typically do questions afterwards or in the middle, but I don't mind you all asking something as we go. So I tend to have a speech impediment. I stutter. If there's something you all don't understand, you can stop me and ask, and I'll do my best to clarify to make sure you're getting the information. So history of metallic fuel is very old, started from whenever the first reactors were done, so back in the 40s. They were of primary interest because of the ability to pack a lot of uranium fuel alloys. They're also a metal, so they have much higher thermal conductivity than uranium dioxide alloys. Where one of the big issues is these things swell like crazy. So this is from a very old study showing a linked increase as a function of burn up for, this is alpha uranium, where we're showing, yes, that is 200% increase in size. These things really, really swell with 10% burn up. So that's untenable in a reactor. So what they started to do is to alloy metallic uranium with transition metals such as zirconium, niobium, moly, in order to stabilize the high temperature BCC phase. So the lower temperature phase of uranium is alpha U, which is an orthorhombic, face-centered orthorhombic structure that is very, very messy and has a lot of anisotropic properties, which we don't want inside a fuel reactor. So they alloy with especially moly and zirc to stabilize the high temperature BCC phase so we can have more isotropic properties. This was able to limit the overall amount of swelling, but these fuels really weren't used that extensively. Oxides caught on in the late 50s, early 60s, and then that's what everyone's used ever since then. So probably the reactor that has the most extensive operational history with metallic fuels is EBR-2, which operated out at what was Argonne West, which is now INL. Operated for 30 years or so, that used UPU zirc fuels mainly. So this is a nice picture of the old reactor out at the site. So you can still head inside this dome on a tour if you're ever out there. So just an overview of a list of the primary types of metallic fuels. So zirc alloys, UZR and UPUZR are primarily of interest for fast reactors. So sodium-cooled fast reactors and project, the integral fast reactor that's planned to use UPU Zerk fuel. Here, within the past 5 years, uranium silicide has come back on the board. So long ago, they explored uranium silicide fuels. They had stayed untouched for a long time, and now they've come back online as a potential accident current fuel for light water reactors, basically as a replacement for UO2 in these systems. UMOLY is a research reactor fuel that they're looking at converting a lot of research reactors in the U.S. to low enriched uranium fuels instead of the currently utilized high enriched uranium fuels for proliferation reasons. So, and there's a number of reactors in the U.S. that are being converted, and there's several European reactors that I forget the names of that are utilizing a different fuel type, but it is still UMOLY. That's the main fuel. And then they've looked at a variety of other things that they irradiated and cooked and they didn't like. So they had a uranium fissilium alloy, uranium titanium, uranium niobium, and a bunch of other stuff. But these are the three main fuel types that I'll be talking about here today. So how do I the picture that you all may or may not have seen, but people like me use a lot and probably overuse. It's a multi-scale modeling picture where we have our time scale, length scale, and we build up from electronic structure to MD all the way up to finite element simulations where it's essentially fuel performance work. I'm in this lower length scale box here. So I do a lot of electronic structure work, and I do a lot of MD work as well. That's the primary range of my scope. So I'm very small scale, but we still look at this whole picture in terms of trying to inform finite element simulations from lower length scale models. So I work with a lot of phase field people who are in this mesoscale range, and then we also work with a lot of fuel performance people, which are up on the very high-end scale. So we're trying to gather data here to feed up into the phase field, also to feed up into the fuel performance work. So even though all of the work I'm showing, all the work I've done is very lower length scale, we're trying to feed that up into fuel performance models eventually. So we start on the very low end, so I'm not going to spend a ton of time on this. There are equations that no one wants to see. So first principles calculations are ab initio calculations are directly derived from physics without any kind of assumptions made. So this is calculating the electronic structure of these systems directly from solving Schrodinger's equations. However, in systems such as uranium, where we have 92 electrons, that becomes unfeasible very quickly. So what we do is we apply a pseudo-potential approximation to these systems, where essentially the bulk of the electrons are contained into a core, and then you have a valence section, which is the primary electrons that participate in the bonding. The majority of the interactions and the properties of the element itself are determined by the valence electrons, typically in the kinds of systems that we're looking at. So this is a fairly good approximation in order to where you only have to look at a select number of electrons instead of looking at the entire scope of electrons. So this is in general valid. And then we apply one more approximation to the system, which is the density functional theory, which states that the total energy of the system is determined by the density of electrons. So we're able to get a total energy by the density of electrons. This is also usually valid. This is all well and good. We can get a lot of interesting properties from this type of work. However, it's limited to fairly small systems. We are limited to doing 250 atoms about. You wouldn't want to do systems much larger than that. You're also typically limited to calculations at 0K. There are now some ab initio MD work where you can look at systems at non-zero temperatures as well, but that's still an emerging field somewhat that it still limits your system size. So what we often do is branch scales from electronic structure up to molecular dynamics. So since we're interested in radiation damage interfaces, all these things that are much larger than 250 atom systems, we have to move to larger systems. So, and with that, we use LAMPS as the one that I use. Everyone has their MD code flavor of choice. That's the one that's open source and very user-friendly that I like to use. So in MD, we're basically solving Newton's equations of motion. How the particle interactions are determined is by an interatomic potential determining the energy of the system as a function of R. So as a function of the distance between the atoms that are interacting. And you can have many body interatomic potentials as well that can have angular components to the system, where you can have complex bonding where all these interactions are described. So back to fuels that we're looking at. So if I had showed you this list of interatomic potentials for uranium a decade ago, it would be blank. There would be nothing. So now we've actually been able to, or there would be one, I think, yeah. So we've been able to develop a bunch of interatomic potentials for the uranium and uranium alloy systems. My name is on a handful of these. I've helped on several. So we have the ability to do MD work now, in addition to the electronic structure work that's been ongoing. This list is much shorter than it probably should be or needs to be in order to describe all the systems that we have interest in. But this is a good start that allows us to do sufficient work to inform higher length scale models and to uncover a lot of the underlying physics and behavior of these fuel systems. So specifically UZR fuels now. I mentioned sodium cooled fast reactors. Why are they used necessarily? They can create a harder neutron spectrum compared to oxide fuels. They've been shown to maintain integrity up to much higher bursts than what oxide fuels have shown. There's a reduction in FCMI due to reduced smear density of the fuel. And they've been explored often to breed or burn fuel in terms of incorporating minor actinides into the fuel to burn waste, or putting fertile material in the fuel to make more fissile atoms. And these fuels are also inherently safe. However, we have some experimental data, but a lot of the properties are not known. What they've done typically with these fuels is that they explored them back in the 60s and 70s, and they stuck them in a reactor, and they burned them for a long time, and then they pulled them out and saw how they look. And so we kind of generally know how they behave, but we don't know a lot of information about why they behave that way or what's happening along the process. We kind of know endpoints. So there's a lot of bulk burn-up data, but there's not a lot of microscopy data, because back whenever these fuels were being irradiated, microscopy was being invented, basically. So we have a lot of optical stuff, but that's about it. There's a lot of new techniques that can be applied, that are being applied to these fuels, but we don't have data on them yet. So one other issue is that experiments typically need to be carried out at high temperatures in these systems. Whenever the fuel's in the reactor, it's very hot, and that complicates things whenever you're dealing with the radiated materials, high temperatures in these systems. You just end up with very complex experiments, very expensive experiments, and so people try to avoid them if possible, unless you're very lucky or at a specific part of a lab. So we try to fill in gaps via modeling. Modeling is much cheaper than experiments, and we're able to get answers much faster. So what kind of a system are we dealing with here? I like to show phase diagrams of the systems that I look at. Some of you all may have never seen phase diagrams. I don't know. But so what we're looking at here, this is the alpha phase of uranium as stable below 776C if you don't alloy it with anything, and then you transfer it to this gamma phase temperature, BCCU, which still doesn't have a very high melting point in these systems, which is why we alloy with Zirc to increase the melting point in addition to stabilizing the BCC phase. So we typically look at alloys of 10 to 20 weight percent Zirc, so we're looking at 23 atomic percent Zirc. So we're typically dealing in this region. where we're kind of in a temperature range that spans a bunch of different phases. So we end up getting very messy systems where we have the BCC phase, and it's the primary phase of interest, but it's not the only phase of interest. Then we have a miscibility gap that we deal with. So then we have a gamma 1 and a gamma 2, and then we end up having even a little bit of beta phase and some alpha phase and some delta phase sometimes too. So this can be a very complex system, even though we're stabilizing the high temperature BCC phase and the kinetics are pretty sluggish, so we can quench it down a bit. You still end up with a very complex system. So this is an example of a optical micrograph that we have, where one thing I'm emphasizing is the changes in microstructure, how complex this fuel actually is, and how hard of a problem this actually is to solve. So here are these curves. This is electron micrograph data, I think, where we're showing the composition of various elements in a UPUZR fuel pin. So here's our plutonium content. That's about uniform throughout the system. However, we're seeing an enrichment in the interior zone of the fuel of Zirc. We're seeing a depletion in an intermediate zone, and then about the ASFAB composition of Zirc on the exterior. So we're getting zirconium to diffuse up the temperature gradient as the system is evolving. And so we're getting zirconium enriched, which has a higher melting point. We're getting zirconium depleted systems, which have a lower melting point in these systems. And of course, if you're changing the composition of these phases that you're dealing with, you're getting different thermal properties, you're getting different elastic properties, you're getting different defect properties that are changing as we change in R. And we're getting different phases as we change too. We typically have alpha here on the edge, and in the center we have gamma, we think. In the intermediate we have beta, we think. But I say we think because we aren't really sure. So, and there's a lot of different phenomena of interest in these fuels. So we're interested in looking at the fundamental swelling rate. We know how much these fuels swell at the end, but there's a lot of scatter in the data on how fast they swell. We know that they swell very fast, and then it kind of plateaus. But the exact rate of that initial swelling is not very well known. It depends on your compositional profile. It depends on the temperature of the system that you're looking at. It depends on the flux that we're looking at. So there's a lot of unknowns here that we're dealing with that we make knowing the fundamental swelling behavior very challenging. Don't know really anything about nucleation of bubbles. We were able to look at the fuel system at the very end to kind of see what the end result of the bubbles are. We don't know how they got there. We don't know if they're coarsening and growing or if there's constant nucleation of bubbles as we evolve in the system. We don't really know the elastic response of the system. We have one measurement of the bulk modulus of BCCU. We have one measurement of the elastic constants, at least the full elastic constants of alpha uranium. There's issues and questions about the phase stability in these systems, about how the TTT diagrams are constructed, and if some of those results are questionable. There's theorized Sur-Ray diffusion of Zirc up the temperature gradient that we think is a thing. We don't know if it's a thing. And then there's a variety of interfacial properties that we don't have any idea on in these systems. And then that's before we even get to these huge holes that form and these kind of other microstructural features that we're dealing with, including FCCI and whatnot. So there's lots of issues here, lots of things that we're trying to explain and explore. So here's one slide of a bunch of stuff that I did on an ab initio scale in UZirc fuels. So here we're looking at the alpha phase. So we've gotten the equilibrium structure of the alpha phase. We've identified the lowest energy point defect location in the alpha phase, which was the first time that was ever done. We investigated the beta phase as well, which I didn't show before, and no one had looked at the beta phase at all because it's even more complex than the alpha phase. It's a 30 atom unit cell that we're trying to explore. It's very, very complex system. We've looked at intermetallic structures of uranium and zirc and uranium and different fission gas species in order to develop interatomic relationships between the uranium and these other elements. We've looked at the density of states of the alpha, beta, and the gamma phases to see how the F electrons, which are dominant in the binding of these systems, how they vary between the different phases. One of the main accomplishments of my graduate work is doing the first point defect formation energy calculation in BCC uranium systems. So BCCU is mechanically unstable at 0K. So whenever you're doing work in DFT, it's inherently at 0K. So if you introduce a defect into these systems, you're going to have mechanical deformation of these systems. You're going to have decomposition of the crystal structure. So what you have to do is you have to impose certain constraints on the number of atoms and which atoms are able to move and evolve in order so that you can approximate what the defect formation energies are. And so we were able to look at a number of defects in these systems, and they actually compare OK to the one vacancy formation energy experimental work that was done. And then since this table was made, there's been a secondary positron annihilation experiment calculating vacancy formation energy in BCCU, and that result further matches our results from this work. And there were still folks who didn't believe these interstitial energies, because if you notice, the interstitial energies are extremely low for metals. They're half of an EV. That's unheard of. That sounds absurd. You would have such a high population of these defects that you're essentially melting the system. That doesn't really make sense. But we've gone back now in fairly recent work that was just submitted and done ab initio MD. So we aren't making any of the approximations on restricting the number of atoms to move. We're allowing it to free flow and do whatever it does, and the results match up incredibly well. So it's hard to believe, but it's extremely easy to form point defects in these systems, and it behaves almost unlike any other metal that we know of. So uranium's hard and odd. So we've taken all that work and we made interatomic potentials for the pure uranium system first. We've looked at a variety of things. One of the more recent fundamental studies that we've done is looking at the threshold displacement energy in gamma U and alpha U and how that changes. We looked at it at a variety of directions as well, analyzing how low symmetry directions versus high symmetry directions affect the displacement energy, and also how the interatomic potential of choice affects the displacement energy as well. So in this curve, we have our probability of Frankel pair formation as a function of the energy, and we are defining the threshold displacement energy essentially where the probability becomes greater than 0.5, so that it's probable to create a defect in these systems. So for the original uranium modified embedded atom method potential that we made, it yields one number. For the modified system that we implemented, we modified the uranium description slightly, and then we added on a zirconium component as well. It provides a slightly different answer, and then a U-Moly potential developed from a separate group to describe pure U as well, provides a third answer. And we're seeing the results vary by a factor of 2. So threshold displacement energies from 30 to 60. This is a huge change. And that's, if we take these numbers, we usually calculate displacements per atom in reactor or in irradiation experiments. through a displacement energy put into the NRT equations to approximate the amount of damage. So what's the number that we're supposed to use here? So we have to find either some way to narrow down what the actual displacement energy values are, or incorporate for this kind of scatter or error. Because all of these interatomic potentials can do a good job of describing the system. They're all splined to a ZBL function whenever the R is very small. So it's something going on in the intermediate distance range that yields a huge change in the displacement energy properties. So that's interesting but troubling. So we've taken the interatomic potential, we've done higher energy radiation damage studies as well, analyzing the number of Frankel pairs made in these systems. And here we're showing a variety of interstitials around a vacancy core, which is a common pattern that you see in radiation damage work. We've calculated the elastic constants of these systems compared to the one experimental value that we have, and then some other first principles data. And then we were able to look at the bulk modulus and the amount of softening that happens in these systems as well. So, and what's also interesting is that we're looking at it for the 3 different interatomic potentials that we utilized up here as well, and we get a variety of softening behaviors as well. There's a lot of scatter, even though these are decent interatomic potentials that get a lot of information right. This is all very large changes in the amount of softening and in what the bulk modulus actually is. So there's a lot of uncertainties involved here. We've gone and looked at diffusion as well, comparing to the one experimental value that we have for BCCU. So this is the one experimental value. Well, I think there's 2 experimental reports that were done. They were done back in the 60s, and we don't have any data on what kind of impurities were in these systems. And it's, whenever you have uranium, you're going to have impurities in the system as well. But overall, we have some scatter, but we have reasonable agreement with the experimental data on the diffusion coefficients. And then finally, we've incorporated various fission gas species into the uranium interatomic potentials as well. So here I'm just showing xenon, and we're looking at the number of, or the magnitude of the formation energy of substitutional defects and then various interstitials in BCCU. And the purple bars, I'm showing the interatomic potential predicted value compared to the green, which is the density functional theory value. So we agree very well for the low energy systems, which is good because this is the preferential site. And then we have a slightly stronger driving force to actually be in the low energy site. And that's fine. That isn't perfect, but that gives us the right qualitative behavior, even if the quantitative behavior on the interstitials is slightly off. So now I'm going to move to the UMALI system. So here again, I like to show the phase diagrams for the systems that I look at. So here we have 100% U and 100% Mali. We typically deal with about U7 to U10 Mali in terms of the weight percent. So we're looking at somewhere between 15 to 20 atomic percent Mali. So we're kind of in the same region as we were before. However, we also have this intermetallic phase that's much closer in this system. But we are still dealing with primarily the BCC phase. One thing that's nice about UMALI fuels is that it's been known since they were starting to be used that no matter what the initial microstructure is, it reverts to the BCC phase once it's in reactor. We don't fully understand this, but there's some kind of a radiation stabilized phase transformation that's occurring in these systems such that we have effectively pure BCCU or pure BCC UMALI phases whenever we're in reactor, we think. So one thing that's interesting about the UMALI fuels that we're looking at is it's a contained system. So usually we think about fuels We have a buildup of fission products and fission gases in these systems. They form bubbles. The bubbles interconnect, and we have pathways that the gas flows out of the fuel. So that's why we have a gas plenum in our fuel to incorporate the extra gas that's being released from the fuel. In these types of fuels that are implemented in research reactors, we have a U-moly fuel foil, the fusion barrier in these systems that is fully encapsulated in aluminum clad. So all the fission gas stays inside, has to stay inside. So it's a very different kind of situation that we're dealing with. We really need to understand the swelling behavior. We need to understand how the fission gas evolves, and we need to know what kind of effects we're going to encounter from not allowing the fission gas to leave the fuel. Excuse me. So some other features that we have in U-moly fuels. Whenever we make this fuel, it's not going to be pure BCCU. We're going to have decomposed regions, and that's what I'm showing here is kind of folded structure. All right, we have one grain that is BCC U-moly, one other grain is BCC U-moly, and then typically along a grain boundary, we have the structure decomposed into alpha U and this U2 moly structure. So we kind of have these folds where it's no longer the BCC phase. So I mentioned before that this shouldn't matter because in reactor it goes back to the BCC phase. However, whenever it phase changes, you're left with networks of dislocations in these systems. You have either twins or you can have grain boundaries that form. And this is something that we've just this is fairly new research in describing the types of the types of dislocations that we're actually being able to see. So this was seen from experiment, and then we've gone and validated what the experiment saw with the crystallography examinations. So where this is important is that if we're starting the system with an excessive amount of dislocations in the system, we get dislocation buildup and much more quickly. This leads to recrystallization in the system, and faster recrystallization in the system leads to deconstruction of the fission gas superlattice quicker, which is not something I mentioned here, but that's another very interesting feature of these fuels. But deconstruction of the fission gas superlattice leads to very large bubbles in these systems, which leads to lots of swelling. So we want to minimize the amount of decomposition of these fuels so that we're minimizing the overall population of additional dislocations that the fuel is starting with so that we can delay the onset of recrystallization and accelerated swelling behavior. One other thing that causes problems in these systems is the zirconium interdiffusion barrier. So this exists because if it wasn't there, the U-moly fuel and the aluminum 6061 clad would interact a lot, and the fuel would get very weak, and you would have very large interaction zones that fail. So we put this Zirc barrier here to prevent the U-moly fuel and the aluminum clad from interacting. However, we do still have interaction between the U-moly fuel and the Zirc. So we end up getting this very heterogeneous layered structure where we have lots of phases in these systems. So we start from the BCC U-moly system where we have a low moly system that's probably alpha U. We have these precipitates in the system that are moly 2 Zirc and probably U2 as well. Then we have a Zirc-rich section as well, either U-Zirc or U-Zirc2 systems. So we have a lot of different phases as we are going across this barrier. We can also have carbide sit in this barrier. And this is all important because one of the failure criteria for these fuels is debonding of the clad. So we have, if this layer fails effectively and it becomes debonded, we're going to have a buildup of fission gas in this pocket that's formed, which causes a pillow on the outside of the fuel, which can lead to coolant channel blockage and essentially fuel failure. So this is a variety of the things that we're looking at and studying in these fuels. Okay, yeah, now this is one I mentioned of the crystallization of the fuel if we have more alpha U there. So some stuff that we've done. So we did a very fundamental grain boundary study in these systems, looking at the grain boundary energy as a function of the misorientation angle, and looked at a variety of high angle grain boundaries in these systems. We compared to older studies where they tried to calibrate some research with experiments. It wasn't exact, but our results compared very favorably to previous work that was done. The thing that we saw, that we found out is we were able to look at the grain boundary energy as a function of moly in the system. So we see a very sharp increase, a very large increase in the grain boundary energy going from pure U to pure moly in these systems. So we didn't know why we would have alpha D composition in these systems, but what's leading to it is that we're having moly depletion at the grain boundaries in these systems. So moly is leaving because the grain boundaries want to form pure U grain boundaries. So we're having a depletion of moly, which leads to the phase diagram wanting to form alpha U. So it's decomposing from this BCC structure into alpha U because of the driving force of the grain boundary energy. The other thing that we did is try to perform this actively. So instead of just doing a static study on the grain boundary energy and inferring the results off of it, we did a combined Monte Carlo MD study where we're performing switches of atoms and accepting the switch. The energy of the system is reduced, and also accepting it given a certain Monte Carlo probability of accepting the switch. And so we're analyzing to see how the composition of the systems evolve if we're allowed to do much larger compositional changes than what would be allowed through diffusive processes only. So we're speeding up what's going to happen eventually, but we're kind of cheating on our way to make that happen. And the thing that we saw, so I'm showing only moly atoms here. I've deleted all the U atoms just to be able to see it better. And so I have grain boundaries on the interior and on the edges of the system. We have fewer moly atoms that actually exist in the grain boundary region. So we're seeing actively depletion of moly along these grain boundaries within these systems. So all of this matches, all this makes sense, and it explains why we're getting decomposition in our fuels as well. So one more system, uranium silicide alloys. So there was a very large increase in trying to find a way to get additional coping time in the event of an accident after the blackouts at the Fukushima reactor. So U3SI2 is being considered as a replacement for UO2 fuel as an accident tolerant fuel. So the reason it's being considered is we're able to get higher thermal conductivity of these systems. We're able to get a higher uranium density as well, and compared to uranium dioxide fuels. But in order to implement U3SI2, we have to gain a lot of information about it in order to be able to perform fuel performance work on it. So how much do we know about it? Not much is the problem. So there were some early studies in the 60s, but it hasn't really been done until the past 5 years again. So we have some basic properties. We know what the phase diagram of these systems is like. We know what the energy of the system is like. We have a little bit of the thermodynamic info as well. But to fill in some of the gaps, we've worked with people at Los Alamos to do some fundamental density functional theory work to determine a lot of the elastic constants of this system and a lot of the point defect formation energies as well. And where I had a role is I actually took the density functional theory data from Los Alamos, and I was able to make an interatomic potential to describe the uranium silicide system. It's not bad. It does the U3SI2 phase fairly well. It can do some other phases in the uranium silicon system, but it's better for U-rich systems. So we also expanded the U3SI2 interatomic potential to describe xenon as well, so that we can look at a variety of fission gas behavior. So this is an example of some of the information that's been input into higher length scale models. So this is oops, nope, that was a stop button. Okay, there we go. So this is a mesoscale Marmot phase field model of intragranular function of the burn up in the system. So this was able to take into account a lot of the information that we were obtaining from lower length scale models. The issue is this still has a lot of assumptions in it that we're trying to rectify and clear up. One of the issues with U3SI2 is we don't really know how much it swells. So some of the old experimental data showed that it swelled a lot, probably on the order of what we're actually showing here. Some of the newer experimental data that just was out, we didn't have the same irradiation constraints as the old experiments. So we don't really know what's changed, but we do know that it's not showing any swelling behavior now. It's like less than 1% swelling. So there's something that's different. Either the old experiments were very wrong, or there's something that's been changed in the manufacturing process, level of impurities, or the flux that they're using. Something is different so that they're showing dramatically different swelling behaviors. So we're showing results as of now that match the older results. It's possible there's something that's incorrect in the calculation of the burnup of these systems, which we've seen before. So there's a lot of issues still that we're trying to solve. All of the assumptions that are made in these models, we're trying to fill in gaps. So we're trying to gain information to input into these models to try to solve a variety of issues so that we don't have to make assumptions. So we're inputting information such as the diffusivity of xenon into these systems, which we didn't have any results for before. We're being able to determine the intrinsic thermally based diffusion of xenon. We're also getting irradiation-driven xenon as well in these systems. So, yeah, here I show the interatomic potential that I developed for these systems. So this is what this looks like. It's just a table of a lot of numbers. So we have descriptions for the silicon system, descriptions for the U system, descriptions for the xenon system, and then cross-species terms for each system as well. So what all have we done for xenon behavior in U3SO2? We've been able to determine the segregation energy of xenon at different grain boundary types. We're seeing that there is a preference for xenon to sit at the grain boundary in these systems, but the preference is very short range, so it's that once you get beyond about 5 angstroms, the xenon acts like it's in the bulk. We've been able to get void energies of these systems, so I'm calling this a surface energy. The average surface energy can be approximated by looking at a void, and we're showing how at very small r voids the energy of the surface is not at all what it is whenever it's much larger. So we're having variation in the surface energy of the void with the function of r and as a function of t. We were able to get a new equation of state for xenon bubbles in these systems. So here I'm looking at an example system where you can barely see the atoms inside the bubble there. But the red atoms are uranium, the blue are silicon, and then the yellow here that don't show up are xenon atoms in these systems. So what we're doing is we're adding in more and more xenon into these systems to increase the pressure inside the bubble. We can get a pressure as a function of the molar volume for the xenon in these systems, and then we can fit an equation of state to this information. Whenever the molar volume is very, very low, it approximates a van der Waals gas, but whenever we're at fairly high pressures in these systems, there's a significant amount of variance compared to just modeling the xenon as a van der Waals gas, such that, and these are realistic pressures for smaller bubbles in these systems, such that we need to account for the different equation of state for xenon in these systems in order to get the actual bubble evolution in these systems as well, whenever the bubbles are small. So that's the end. I think I still have time. So I've done a lot of modeling in metallic nuclear fuels. It's greatly accelerated over the past 8 to 9 years that I've been able to work on these systems. Whenever I started, nothing really had been done. Now we have a lot of information. There's still a lot of information that we don't know, still a lot of fundamental basic work that needs to be done in order to understand what's going on in these systems. These fuels are very complex, and it's hard to simplify a lot of the models down to very basic parameters that we can put in these systems. So we couple lots of the things that we do with higher length scale models that are capable of analyzing a variety of different things that we're not able to handle from an atomistic perspective. So, and there's a lot of planned experimental work as well that's to explain or validate some of the behavior that we're also looking at here in these systems that will hopefully either confirm the results that we're showing or show us where we're wrong and how we can fix our models. So as the computational capacity is increasing, we're able to do much more complex things. So we're just now, this past year, being able to do AIMD on these kinds of systems, which is AIMD has been around for 20 years. We haven't been able to use it on uranium systems though yet. So now we're just kind of opening that box in order to do a lot more complex, interesting things. So my thoughts is that it's a very exciting time for people doing this kind of work on metal fuels and on lower length scale work. So with that, I'll be happy to take any questions. And yeah, thank you all.
Questions for our speaker today?
Yeah. I'm really not that familiar with uranium sulfide fuels, but are they clad?
No.
They're not
No, they are to replace UO2. So instead of putting UO2 in your fuel, you're putting U3SI2.
Yeah, I know UO2 is clad with zirconium.
Oh, you're asking, yeah. So it's basically the plan is to keep zircaloy cladding on the U3SI2.
Isn't the problem with zirc-clad fuels the metal water reaction? And
Yeah.
you haven't done anything to solve that problem.
Yeah.
Okay,
So-
you
so-
done everything in the bottom of the metal.
So the point is that U3SI2 conducts heat better, so you're removing heat from your system faster. So hopefully, you have less melting. You will have less hydrogen gas formation in these systems. I don't know if that's the case. That's a question for Westinghouse more than is one for me. But that's the other reason why they're investigating FECROL as a possible clad or SIC as a possible clad in these fuel systems. So typically they haven't specifically said U3SI2 with FECROL. They're trying to say U3SI2 with zircaloy clad, but that's flexible. Whatever Westinghouse is planning on doing is what they'll do. But that's a question that doesn't directly affect this research. We're just trying to see what the properties of U3SI2 are that we don't know anything.
I've just heard people talk about using uranium silicides as an action tolerant fuel. It sounds to me like you're addressing the wrong problem.
That's entirely possible. No.
More questions?
About Python, how evolved is it when it comes to modeling like metallic fuel using those like the mesoscale levels and the current level? What is the current progress in Python right now when it comes to those kind of fuels?
So there exist models. Well, there doesn't exist a model for U-moly fuel. So the fuel performance work for U-moly is not being done in Bison, which is some people are arguing about. But for U-zirc fuels, there are swelling models. There are fuel performance models that are there. They are in their infancy. So we are revamping a lot of the fuel swelling models right now. That's one of the milestones that we have this year. And I've calculated a number of properties for UZR that have been implemented into Bison this year. So this is all new. This is all developing. This is the first year where we've had a very strong push for UZirc fuels. So it's becoming very rapid now. So they exist. They do an okay job, but they are generally wrong. So we're trying to improve the models. So
it's early to talk about their validation and their data.
I would say it's way too early for that. They can predict some of the numbers right. So they can get qualitatively the correct amount of swelling, qualitatively the right amount of fission gas release. So they can generally have a ballpark estimate for failure of fuel, but how they get there is way off. So they still have a long way to go in order to have something that is a validatable model, if that's a word. So.
For that happens, do we go like from electronic to the Marmot scale, the microstructure to continuum, or how?
Yeah, so that's exactly the way we're trying to approach the problem. So we know where the issues are in Bison. We know what things that they do wrong. So we're using Marmot to address those issues, or Atomistic work in order to address those problems. And we're trying to feed information up the scale in order to solve the known problems that we have from a fuel performance issue.
Are you calculating displacement energies using those previous simulations? When you had zirconium, there was
Well,
different.
I didn't add Zirc into the system. I used an interatomic potential that I labeled differently because it's able to describe UZR systems. So maybe I should have emphasized that, but that is still looking at pure U, but for different interatomic potentials. But yes, even for just the pure U system, then we're getting very different displacement energies, which is a problem. And I assume if we add Zirc into these systems, it's going to vary as well, but we don't know. We don't know how it varies. So that hasn't been studied, hasn't been investigated at all. I've done a little bit of binary collision Monte Carlo work on pure U versus UZR. That's only going to tell you some information that's approximated from much higher level models. So.
Can you show slide 20? It's white.
Yeah, so that is a xenon atom that I'm looking at. So this is just an example of a U3Si2 system where I stuck a xenon on a silicon site just in order to analyze a xenon on a silicon site substitutional defect. So, and there's 3 different sites within the U3Si2 lattice as well. So there's 3 different, you can see formation energies, 3 different substitutional energies, and then there's any number of interstitial energies as well in these systems.
Any more questions? I've got one quick one. Hopefully, I don't know, it's a really horrible, stupid one. It's kind of, we'll find out. The beginning about how they set up the how you set up the electric potentials for something like uranium, where you have a ton of electrons. You talk about how you break the electrons up into 2 groups, the ones you care about, and kind of like this core kind of. Is that just using like a reduced probability function? So what would we do similar whenever you develop kinetic models and plasmas, where you take you average out some of the electrons, and then you just pay attention to a reduced subset. Is that kind of what they do?
So
like a hierarchy?
Yeah, so really all that they do, so they this is done by people who develop these kinds of things to have the proper electronic response whenever you're reducing the number of electrons. So you just make a core where they are gone effectively, and say an effective core potential in the system that has an associated energy with it. And then the other electrons are out to do whatever. So you have to be very careful whenever you're looking at defects, say. You might have core overlap, and then you're double counting core electrons that are not supposed to be involved in anything. So it's really, they're effectively gone, and they have an associated energy, but they aren't contributing anything else to the system.
Okay.
So.
Thanks. Okay, going once. Going twice. I know someone's going to raise their hand. They always do. No? That's a first. Okay, let's thank our speakers, please.
Thank you all. Thank you.
This one.